Assalamualaikum and good afternoon. We are from Group 1. Today we are going to present about arithmetic and geometric sequence thermal expansion of a piston rod. First, we go to our group member first. From the right side, we got me, Muhammad Hakimi bin Muhammad Zamani. And then we got Muhammad Alif Hakimi bin Nur Isamuddin. Next, we got Wan Muhammad Arif bin Azmi. And lastly, we got Arif Asidin bin Muhammad Zuana. This is the introduction part. In mathematics, a sequence is an ordered list of number that follows a specific pattern. There are two types of sequence. One is arithmetic sequence and the other one is geometric sequence. The arithmetic sequence is constant difference between terms and geometric sequence is constant ratio between terms. Both sequence are widely used to model a real life growth and change. We go to the problem statement and objective slide. Alright, the first problem is how piston rod expansion can be modeled using arithmetic and geometric sequence. And the next one is how to determine the point at which the rod become unsafe. And the objective here is to apply arithmetic and geometric sequence to predict piston rod expansion. And the other one is compare both models to determine which better represent the real world behavior.
Now, I will explain each figure table which connect a real engineering situation. I will make it simple. A piston rod is an engine with mathematical concepts such as arithmetic and geometric sequences. From the first column is the fact. Here are the facts you know. A piston rod is used in engines and machines. The engine operates, the piston rod become hard. It causes the metal to expand. So, the length of the piston rod increase. This process happens repeatedly after every operating cycle. However, the piston rod has a maximum safe length. If it becomes too long, it can be unsafe or damaged. Now, we move to another column, the ideas. From this fact, we get several ideas. The piston rod length increase after every cycle. The increase might be the same each time, or it might become less over time. If the increase is constant, we can model it using an arithmetic sequence. If the increase grows over time, we can model it using a geometry sequences. So, mathematical models can help us predict when the piston rod become unsafe. Now, we move to another point. Another column is learning issue. From here, we have some questions to explore. How does thermal expansion happen in practice? How can we apply arithmetic sequences to model the expansion? How can we apply geometric sequences? And most importantly, which model better represent the real behavior of the piston rod? And now, the last column is action plan or resource need. To answer this question, we plan to first define the initial length of the piston rod. Second, assume the expansion rate for each operating cycle. Third, apply arithmetic sequences formulas to calculate the length after each cycle. 4. Apply geometry sequences formulas for the same purpose. Finally, identify at which cycle the rod exceed the safe length, compress the result, and draw conclusion.
Okay, so for result and calculation, for part A, arithmetic sequence, there have an anthem and sum of the first anthem. So the anthem, the formula for the anthem is Tn equals to A plus n minus 1 times with T. There is A is a first term, n is a difference, the difference, and D is the common difference. Then sum of the first anthem for the formula is Sn equals to 2A plus n minus 1 times with D. So for first questions, the extensions at cycle 15T, for it's given A equals to 100 and then D equals to 0.8. So we use the formula and term, so that T in bracket 15 equals to 100. There is a first term, then plus with 0.8, there is a common difference, and 15 minus 1, there is n minus 1, 15. The term minus with 1. So the answer is 111.2. Then the next question is the total extension after 15 cycles. There is 15s. So it's given like before, A equals to 100, then D equals to 0.8. So we use all of them. By other formula, there's sum of the first anthem. There's Sn equals to n2 times with 2A plus in bracket n minus 1 times D. So we just put by data given before, like S in bracket 15, then equals to 150. There's actually 15 over 2, then is times with 2 times with 100, then plus 15 minus 1, there's n minus 1, times with the common difference is 0.8. So it got like 152 times with 211.2. Therefore, the final answer will be 1584. Okay, then we move to the next question, is number 3. The average extension per cycle up to 15 cycles. So first of all, we use the Sn and then times with n. So therefore, it will equals to 158,415. Then it equals to 105.6. Okay, so for the fourth answer, the first cycle n greater than equal m. Therefore, they're given a the first term is 100 and the common difference is 0.8. Then the m equals to 112. So we use the formula Tn greater than equal m. So we just put inside 100 and 0.8 that given. We use the Tn formula before, like Tn equals to a plus n minus 1 common times with common difference. So we just put all inside. Then we got the n minus 1 will be subject. So we make the n minus 1 make the subject. Then we put the m data. Then the negative 1 to the right hand side. Then n will be the subject. So n will greater than equal 112 minus with 1000.8 plus 1. Then there will got answer n greater than equal 16. So n is 16, around 16, like that. So then we need to construct a table, Tn and n as for sum of n for 20 cycles. So there's a table Tn and Sn for 20 cycles. So we just put all inside the table up to 20 cycles, followed by the question given. It actually it need used by manually and Excel, but we just put Excel because manually it just like equation for this all data. So we not put in the slide. It just in our report. We make a graph for Tn with n, and we got at the upright of the graph, you can see there's a Tn with n graph. Then at the bottom, we can see S sum of n with n. So there's the graph. Okay, so then we move to the result and calculation for part B. There's a geometric sequence. So it's given two formula for this sequence. There's a Tn equals to AR to the power n minus 1. Then the next formula is sum of n term equals to A in bracket 1 minus R to the power n, close bracket, over with 1 minus R. Then R will be R less than 1. Then R also cannot be a value of 1. So the first question is the extension at cycle 15. There's a 15t. So we use the geometric progression. There's t15 equals to 100. Then we will just put the 1.008. There's a common ratio for geometric progression. Then to the power of 15 minus 1, there's n minus 1. So it will got 111.801. Then this, the next question is the total extension after 15 cycle. There's 15s, sorry. So the S15, the sum of 15 will be equal to 1001 minus 1.008151 minus 1008 and equal is 1586.983. Then the third question is the average extension per cycle up to 15 cycles. So the S and N equals to S will be equals to S15 and equals to LS15. So it just 1586.98315 will be equals to 105.799. So for the last question is Tn greater than equal to M. So 100 will be times with 1.008. There is we just put the AR to the power n minus 1 formula. Then we got equals greater than equal 112. So that n minus 1 will be converted to ln. Then it will times with 1.008. There's a common ratio. Then greater than equals to ln because we put ln both sides. There's ln 112 over 100. Then n minus 1 greater than equal ln 112 100 ln 1.008. Then n will greater than equal ln 112 100 ln 1.008 will be plus 1. Then n will be greater than equal 15.223. So n should be 15. Then for the we need to construct a table Tn and sum of n for 20 cycles like before for the geometric progression. So there is a table for Tn and sum of n for 20 cycles. So we can we just arrange the Excel table. We not put a manual table because manual table is so compact. So we just give the answer for show the graph later. So then we move to the graph. It show a graph graph Excel. Then there's two graphs. There's a Tn with n like before. So we can see at the up right of the graph, we can see the Tn and n, then at the bottom we can see sum of n with n. We go to part C, there is a comparison. So the first one is a comparison between arithmetic and geometric. So there is not have bigger difference because it just like the same a bit. But we can see at the number 2 comparison between sum of n arithmetic and sum of n of geometric, we can see there's totally different because for the red color, sorry, for the orange color, there should be for arithmetic, and the green color should be for geometric. So it plot differently, and maybe it just have different at the sum of n term graph, not at their n term arithmetic or geometric progression.
Today, I will compare the arithmetic and geometric models and explain their impact on the piston rod safety. The geometric model shows faster growth because it's increased it based on compounding, while the arithmetic model grows at a constant rate. As a result, the geometric model reaches unsafe condition earlier and provides a more realistic warning for potential failure under repeated hitting. This result implies that repeated hitting can weaken the material, cause dimensional change, and increase the risk of misalignment and failure. Performance is also affected through higher friction, reduced efficiency, and shorter component lifespan. Several factors influence outcomes, including operating temperature, material strength, design tolerance, load, environment, and manufacturing quality. To reduce the risk of damage, engineers can use low expansion material, design expansion gaps, control temperature with cooling system, apply suitable lubricant, and perform regular maintenance. Overall, the geometric model better represents real operating conditions and support safer engineer decision. Conclusion: this study has shown that arithmetic and geometric principles play a vital role in engineering, analysis, and design. Through mathematical modeling, numerical calculation, and geometric measurements, we use to evaluate dimension, quantities, and relationships that are essential in solving engineering problems. The result demonstrates that even simple arithmetic operations and geometric concepts can produce accurate and reliable solutions when applied correctly. Mathematical modeling is especially important in ensuring engineering safety. By using arithmetic, calculation, and geometric modeling, engineers can predict loads, distance, areas, volume, and structural behavior before constructions begin. This helps to reduce that design meets safety standard and functional requirement. From this study, it was learned that mathematics is not just theoretical, but a practical tool for engineering problem solving. Arithmetic provides precision in calculations, while geometry help in visualizing and designing real-world structures. Applying this mathematical concept improves accuracy, efficiency, and safety in engineering practice. Overall, the project highlights the importance of mathematics as a foundation for effective and safe engineering solutions.